Today, during period 4, a really important question was asked. Why can we use KW equals KA times KB in the second half of the 2009 problem? To answer this question, we need to know what KW really means. It starts off by studying something called the dissociation of water. In water, a certain natural amount of the water molecules are going to break apart. We can assume that one of them will split into its basic pieces. The hydrogen ion will attach to the second water molecule, producing an H3O plus hydronium ion. Then the other hydroxide ion will remain by itself. To write the equilibrium expression for the water, you totally forget about the liquid water and you only write about the hydronium ion and the hydroxide ion. Now keep this expression in mind for later. In the 2009 problem, we are focusing on a molecule. We're focusing on HOCl. Now sometimes if HOCl is on the left side of the equation and it reacts with water, it will behave like a weak acid, producing hydronium and OCl minus. When OCl minus is by itself, it does the opposite thing. It will react with water to produce HOCl and OH minus. One of these acts like an acid, and one of them acts like a base. So let's write the Ka and Kb values for these guys. The Ka of the first equation would be hydronium times OCl minus divided by the HOCl concentration, and the Kb will be OH minus and HOCl divided by the OCl minus. Now, I'll tell you a true fact right now. KW is equal to Ka times Kb. And here's how we prove it. If you multiply the two expressions for Ka and Kb, things start canceling. The OCl minus is cancel, and the HOCl's cancel, and all you have left are the hydronium ions and the hydroxides. And that is why Ka times Kb is true for any species that involves the same weak acid or weak base and its salts.